Before we finish with plan space search, I want to introduce another refinement to the generic algorithm we've just seen. This is the algorithm as it was implemented in the PoP planner that was developed in about the early 90s, if I remember correctly. In the algorithm as we've seen it so far, it considers two types of flaws: unachieved goals and threads. And every time we go through our main loop, one of these flaws is removed from the plan and potentially others introduced. The PoP planner only considers unachieved goals and deals with threads as part of the main loop. So here is the data flow of the PSP algorithm as we've seen it so far. We start off with our initial plan pi0. That plan consists of actions, orderings, bindings, and causal links. Then what we do is we compute the threads and the open goals, which are the flaws in our overall plan. Then, if we find there is no flaw in our plan, we can return this plan as a solution plan. However, if there are flaws in the plan, then we've got to select one of these flaws, compute the resolvers. If there are no resolvers for the selected flaw, then we can return failure, because this plan can never be refined into a solution plan. If there is a resolver, then we've got to choose one of the resolvers that are possible, apply those resolver, and while we apply the resolver, we've got to maintain our ordering constraints and our binding constraints such that variable bindings and orderings are always consistent. Then we go back in our loop and start at the beginning with the partial plan that we consider. The PoP planner is different in that it does not deal with the computation and handling of threads at this stage in the algorithm. In fact, threads are moved to a different part, namely after the open goals are dealt with, the algorithm will deal with all the threads that are caused by the resolver for the open goal flaw. And this may cause a little loop here, namely one where all the threads are dealt with. The input to the PoP planner, or to the PoP planner to be more specific, looks slightly different from what we've seen so far. We have an extended input that takes a partial plan as input. That is the same initial plan we've seen before. And the second component it takes as input is an agenda of things that still need to be done. And as this is a set of pairs of actions and preconditions of these actions. So these are all the open goal flaws that exist in the current partial plan. Initially, that is of course all the preconditions of the goal dummy action. The agenda is simply the way to avoid recomputing the open goals every time we go through the loop, where the loop here is implemented as a recursive function. Search control of the algorithm is then by flaw type. That means we have the unachieved sub-goals as part of our agenda, and every time we go through our algorithm, we go through the loop, we select one of the unachieved sub-goals and remove that as a flaw from our partial plan, potentially introducing others. Threads, on the other hand, are resolved as part of the successor generation. So internally to the algorithm, we remove all the threads so that when we generate a new search node, that will have no threads in it. Finally, we get to the pseudocode for our partial order planner. This is essentially the algorithm that is implemented by the PoP planning system. Unfortunately, the algorithm is a little more complex than the algorithms we've seen previously, so I had to distribute it over 2 slides. So this is the first part of the algorithm. And what we define here is a function PoP, which implements our partial order planner. And this function takes 2 arguments. Firstly, a partial order plan, which initially is our initial plan pi0, and it takes an agenda, which consists of all the unsatisfied sub-goals in our current plan. In our initial plan, these were only the preconditions of the goal dummy action. Then the algorithm begins by testing whether the agenda is empty. So if there are no more unsatisfied preconditions, that means our plan contains no more flaws, and that means it's a solution plan for our planning problem, and we can return this plan as a solution. However, if there are still items left on the agenda, then we need to select one of these as the flaw we want to work on next. And the selection is a deterministic choice point, which means we don't need to backtrack over it. The reason is, again, that we need to work on all agenda items eventually, and it's only important for efficiency in which order we do that, but not for completeness. So now we've chosen a pair, which is an agenda entry, consisting of an action AG and a precondition PG. The next step simply removes the chosen entry from our agenda. Then we have to compute all the providers for our chosen precondition PG. A provider, of course, can be any action that has an effect that can unify with PG. This could be an action that is already in the plan, or it could be a new instance of an operator that we introduce into the plan. So this gives us our set of relevant actions. If this set is empty, if there are no relevant actions, then there is no way to resolve this flaw, which means we can return failure. So what we do at this point is go up in our search tree to the nearest backtrack point and try an alternative branch. Now, if our set of relevant actions wasn't empty, then we can do this now and we can choose one. This is a non-deterministic choice point, which means here we set up a backtrack point where we branch in our search tree. And if any of those branches returns failure, we simply go back and explore the next branch. Choosing a resolver gives us three things. Firstly, it gives us an action that we've chosen as the provider. It gives us a proposition that is one of its effects that unifies with our unachieved subgoal, and the substitution sigma is the substitution that makes the unachieved subgoal and the effect the same. Given our chosen resolver, we can now start to refine the plan accordingly. And the first thing we do is we add a causal link. And the new causal link links our chosen provider, AP, to our consumer, AG. And the proposition that we're trying to protect is sigma of PG, the instantiated goal proposition. Note that this is the same as sigma of PP, as sigma unifies the two. And in addition to this causal link, we also need to add new bindings to our variable binding constraints, and those are exactly those bindings that are defined by the substitution sigma. This is the first part of the algorithm, and the next part follows in the next slide. So far we have added causal links and variable bindings to our partial plan as necessary. The next component we want to modify in our partial plan is the set of actions. And this depends on whether our chosen provider, AP, was already an action in our plan, or whether it is a new operator instance that we introduce into the plan. If it is a new instance of an operator, so if it was not an element of our plan, then what we have to do is simply add that new action to our plan. And we also have to add to the agenda all its preconditions as unachieved subgoals. If our chosen provider was already part of the plan, then we don't need to modify the set of actions of our partial plan. In the next step, we simply generate a copy of our plan that we can modify in the loop that follows. As I've explained earlier, the introduction of new actions or new causal links into a partial plan may also introduce new threads. And this is what we will deal with next. So what we have here is a loop over all potentially new threads. These are threads on our newly introduced causal link or threads that are due to the new action. Of course, if this was an existing action, this cannot introduce new threads into the plan, but we can always have threads on our new causal link. So, for each of these threads, we have to compute the set of all possible resolvers for this thread in our current plan. And if there are no resolvers for one of those threads, that means we can return failure because there's no way of removing that flaw from the plan. Again, returning failure here means going to the next backtrack point and trying a different branch in the search tree. If there are resolvers, then we need to choose one of them. And again, this is a non-deterministic choice point, which means we may have to backtrack to this point. If we fail in one of the branches, we go back and try a different branch until we reach one where we succeed. And then we take our resolver that we've just chosen and apply that to our current plan. So we take the new plan and refine it according to that resolver, which gives us a modified new plan. And then we can simply do the recursive call. So we call our procedure PoP with our new plan and our modified agenda. And of course, our new plan only contains flaws of the type unachieved precondition, as all the threads have just been resolved in the loop we've just gone through. And the agenda contains all those unachieved preconditions. And that concludes our partial order planning algorithm, and it almost concludes this segment. Now, Before we finish with plan space planning, here's a quick overview of how plan space planning compares to state space planning. Firstly, in state space planning, we are dealing with a finite search space. In each state, we only have a finite number of objects, we have a finite number of relations, which means there's a finite number of atoms that can relate the different objects to each other, and that means there's only a finite number of states that we have in our search space. In plan space planning, on the other hand, our search space is potentially infinite. You can easily see a plan can have potentially infinite length, so there must be an infinite number of plans in our search space. But of course, what matters in practice is the part of the search space that is generated or that is explored before a solution plan is found. And also, in state space planning, our search space is usually a graph, but what we're searching is a tree, and the tree is infinite. But what we do have in state space planning is an explicit representation of the intermediate states that we're going through on our way to the goal. In plan space planning, during the planning process, we don't know which intermediate states we will encounter. This is quite an important distinction, as we will see later in the course, because most of the modern heuristics that are used during planning rely on an explicit representation of the intermediate states that we are searching. So the heuristics are defined on states, on world states. Next. In state space planning, the ordering of the actions really reflects the search control strategy that we've been using. Whereas in plan space planning, the choice and the organization that we have in our plan is independent of our search strategy. So in state space planning, we consider one action after another, and the ordering in which we consider them is also the ordering in which they end up in our plan, even if there is no ordering constraint necessary between these actions. In plan space planning, we are much more flexible. In fact, we have seen that in partial plans, two actions in the plan don't necessarily need to be ordered with respect to each other. They can be in parallel. Also, in plan space planning, we have an explicit representation of the rationale why actions are in the plan that is given by the causal links. There's no such structure in state space planning. We only have the sequence of actions that we need to execute. This is quite important for the execution of the plan, namely when things go wrong. If we then have the explicit knowledge of why we did an action, then it is much easier to fix the current plan. And finally, in state space planning, the search nodes we consider are relatively simple. That is, each search node is a set of ground atoms, and the successors were relatively easy to compute. I say relatively easy because there may still be an exponential number of applicable actions, of course. But in practice, this is rarely the case. In plan space search, on the other hand, the search nodes are quite complex, meaning that we have constraint networks that we need to maintain as part of our refinement process. So that means successors are potentially expensive to compute. Overall, one can say that plan space planning was a big step forward when it was introduced, but nowadays, due to efficient heuristics, state space planning is the more efficient way of searching for solutions. This concludes the segment on plan space search. In this approach, we have introduced a new search space in which search nodes are partial plans and steps in our search space are plan refinement operations. This is, of course, completely different from the search space we have considered during state space search. That means we also had to define a new initial state and a new goal test. And what we did in our PSP algorithm was search for a plan that has no flaws, where a flaw can be either an unachieved subgoal or a thread. And finally, we've looked at a refinement of this generic algorithm that was implemented in the UC PoP planner, where the only flaw we considered were unachieved subgoals, and threads were dealt with as part of the node generation process. And that's all I was going to tell you on partial order planning.